So today we're going to cover differentiation, which arguably would be the most important skill an economics major has to know, because you will find that most of the courses in economics would use differentiation. It's more important than than linear algebra, because linear algebra, you only see it in econometrics, one course in undergraduate level economics. It's more important than integration because you are very unlikely to see integration. Maybe in macroeconomics and statistics, but not necessary. So you don't necessarily, so integration is not something very common to undergraduate economic studies. Differentiation, on the other hand, there is just no way of avoiding it. Every single course, beyond the most basic ones, would use differentiation. So it's the most important skill that you need to learn. Okay, so this is where we left off last week. We were saying that you can approximate the slope at a particular point A of a function by using a two-point formula. Now we want to do that because without calculus, we only have two-point formula to find a slope, and two-point formula is only accurate for straight lines. In economics, you typically see curves like that. And how do you find the slope for a curve when you only have the formula for a straight line? What we can do is to use approximation. You pick a point on the curve and use 2 points to find the approximate slope. The approximation is not very accurate if you pick a point that is very far away from the point that you are interested in finding the slope for. So, like if you pick this point to find the slope for the red point, they are very far away. So you can see that the green line, which represents the slope you can find with two-point formula, it's very far away from the real slope that you're trying to calculate. You can improve the approximation by moving closer and closer to the point you're interested in, and the approximation is completely accurate if the 2 points are identical. So if you use the two-point formula with the same point, then it's supposed to give you a completely accurate estimation, except the two-point formula does not work when you have 2 points that are the same. Right? You get 0 over 0 since the 2 points are the same. So you can't really use two-point formula on the same point. Instead, you have to use the limit of the two-point formula. We see that there's a trend that the approximate slope is getting more accurate. It seems reasonable to assume that the approximation would be the most accurate when it's exactly at the point. But you can't use the two-point formula directly, so you instead look at the trend. The trend does exist when the 2 points are identical. The actual formula does not work, but the formula for the trend of the slope does work. So even though the fx minus fa over x minus a does not exist, is undefined at this point, the limit of it does exist. And that's the slope that we are looking for. So this limit of the two-point formula it's the basis of what we're going to do today. And you often see an alternative formulation, which represents the exact same thing, but it's sometimes easier to work with. So let x equals to x minus a. And that means that x would equal to a plus h. Starting with the limit of the two-point formula, you can substitute in a plus h for x. Then you'd get limit a plus h to, approaches a, f a plus h minus f a over a plus h minus a. Cancel out the a's that you can cancel out. You get this formula. The limit as h approaches 0 of fa plus h minus fa divided by h. This formula you see a lot in calculus textbook. It comes from the it comes from the limit of the two-point formula. So they're representing the same thing, it's just a switch of variables. This expression is called a derivative of the function f at the number a. And it's usually denoted by f prime a. When you type the mathematical notation, it's f single quote bracket a, but you pronounce it as f prime a, f prime a. So that's the mathematical notation, and in English it's called the derivative. The derivative usually refers to this term here, this term. However, as we just said, it really just comes from the limit of the two-point formula, so you can equally say the derivative is the limit of the two-point formula. So limit is the derivative is the limit of the two-point formula. All right. So you could use the limit directly to find slope at a particular point. There's no, you can do that. So let's say you want to find the slope of x squared minus 8x plus 9. This is a quadratic equation. This is a quadratic equation. And you can imagine that when you have a quadratic equation, right, that looks something like that. The slope would be changing at different points, right? The slope would be different at different points. And at some of the points, using a two-point formula directly to approximate would be quite inaccurate. So here's the point where the derivative can help us a lot. So slope at a would equal to the limit as h approaches 0 of f a plus h minus f a over h. When you write down this step, there's a question. Should you use this h? You should use this second alternative formulation where you have h instead of x, or should you use the original limit of the two-point formula? You would see that the textbook use both, because one is sometimes more convenient than the other. There's not, it just depends on the situation. Most of the time, you're going to use this version, because most of the time this is more convenient. But some other cases, as you'll see, we have one case later on, it's actually easier to use the original limit of the two-point formula. Okay, so limit as h approaches 0 of fa plus h minus fa divided by h. You substitute in the formula. So fa plus h would be a plus h squared minus 8a plus h plus 9. So that's the first part. Minus the second part is fa, so that's a minus a squared. Oh, let me put it in a bracket. Minus a squared, and then you have the 8a, and then the 9 divided by h. What can you cancel out? The 9 can be cancelled out. 8a can be cancelled out. So you're left with a plus h bracket square minus 8h over h. You can expand this term You can expand this term, right? Oh, a squared, sorry, you're right. You can expand this term, and the a squared would actually cancel out. A squared plus 2ax plus x squared minus 8x minus, yeah, that's correct, minus a squared divided by h. Right, so clearly a squared cancel out, and notice that you have h on for all terms on the numerator, and you also have h in the denominator, so you can cancel out the h. You're left with limit as h approaches 0 of 2a plus h. Here's the point where you can use direct substitution rule. Remember that if you have a polynomial or a rational function, and you are trying to calculate the limit of that function, you can just directly substitute what value h is approaching into the function, and that's the limit. So in this case, this is a polynomial, right? This is a polynomial of order 1 with respect to h. So this is a polynomial. 2a is a constant. H is the variable. So this is a polynomial of order 1 with respect to h. You can use the direct substitution rule. So you substitute in h equals 0 into the formula, into the function. And then that gives you 2a. Oh. Yeah, it shouldn't be 2a, right? Let's see. What did I cancel out? So a squared, 2a plus h minus h. What did I do wrong? What's this supposed to do? 2a, so that should be an 8. Yes, that's right. There's an 8 here. Yeah. Okay, that's 2a minus 8. So that's correct. That's correct. This is correct. Yeah. So you cancel the h, 2a. Yeah, that's correct. Right. So that gives us a slope. This is a slope for any point A on the quadratic function. You can use this formula to calculate the slope at every single point. It takes us a few steps to calculate, to derive it, to get there. What we do today is to figure out the patterns between the particular functional form and the slope you get. Turns out there are patterns that you can memorize, and after you memorize the pattern, then you just not deal with limits ever again, because for us, what we want is a slope. So if there are patterns that you can memorize, once you see this function, you can pretty much directly conclude that this is what the slope is going to be, and then you just skip all the step in the middle. But even though that's what we do, it's important to at least recognize that the rules that we use comes from limit. Right? All of the rules that we're going to see today can be derived with limit. So since the derivative is a limit, it does not necessarily exist. As we have seen last time, limits do not exist if the trend from the left does not equal to the trend on the right. So there are cases where the limit does not exist. And since the derivative is a limit, that means that it's possible for a derivative not to exist. A function f is differentiable at a point A if the derivative exists at that point. the function is it's differentiable at everywhere if it is differentiable at every point in this domain. So differentiable function is almost always the type of function you're going to see in economics. We typically assume functions to be differentiable. Why? Well, because if the function is not differentiable, that means you can't use the derivative to find the slope. And given how important it is to find slopes in economics, we want to make sure that we can use it. So that's the mathematical reason. Like, we want things to be easy. But is it realistic? Well, is it realistic for us to assume that functions are differentiable in economics? So let's look at what functions are not differentiable. So what functions are not differentiable? A function like this one would not be differentiable. Let's use a okay. A function like this one would not be differentiable. It's not differentiable is because if you look at the approximate slope from the left-hand side and the right-hand side, one is upward sloping and the other is downward sloping. The approximate slope from the two sides are completely different, and it doesn't help. It doesn't improve. They don't get closer, even if you use very close points to do approximation. If you imagine you scale up this point in the middle, you're still getting a corner, and the approximate slope from the two sides are still going to be one positive, one negative. They're never going to be equal. In this case, the limit of the two-point formula doesn't exist, because if you use two-point formula on the left-hand side, you get a positive slope. If you use the two-point formula on the right-hand side, you get a negative slope. So the limit of the two-point formula does not exist when the two sides cannot agree. So you have positive slope here and negative slope here. So you clearly the limit of the two-point formula does not exist. Since the derivative is the limit of the two-point formula, the derivative does not exist. The existence of a limit is relative to a point. So the existence of differentiability is also relative to a point. What this means is you can't use differentiation to find the slope at this very point at the top. This very point at the top, you can't. But everywhere else, you can. So in some cases, you can get away with this problem by saying that the function is differentiable everywhere except at a finite number of points that you don't care about. Like this one. There's one single point that you can't use differentiation. Maybe it's okay if we are not interested in this point. So that's one example that you can't use differentiation. Is it okay if we assume that this does not happen in economics? In economics, what functions do you typically need differentiation for? Basically, utility and profit. So is it realistic to have a utility function or a profit function that looks like this shape? Just before I proceed, is there anyone who doesn't know what utility is? Right? Some of you might not be econ majors. So utility is, you can just imagine this is how happy you are, right? So the horizontal axis will be measuring the things you have. The vertical axis will be measuring how happy you are. So you can imagine utility function typically should be going up with things you like, and it should be going down with things you don't like. Okay, so that's utility. Let's imagine this is money, right? Everyone likes money. So let's imagine X is money. Is it realistic to have a utility function that goes up and then very sharply comes back down? So it's like saying you are very happy when you have more money if the amount of money is below $9,999, and then you suddenly hate money when you have, or you suddenly start hating money when you have $10,001 or more. That doesn't sound very reasonable, right? Why would you be very happy with money when you, and all of a sudden, just because of $1 more, you hate money? It doesn't sound reasonable. Now, there are things that you might like with a small amount and hate with a large amount, right? What would be a good example? Like a small amount of table salt is something that we need as human. Large amount of table salt is going to make food really, really bad, right? So table salt would be something that you like for a small amount, and gradually you don't want more of it, right? You start hating it. You don't want a lot of salt in your food. So, but that's change, right? I think that's reasonable. With a small amount of salt, the food tastes better. But with a large amount of salt, the food tastes really bad. So at some point, you actually get less happy with more salt. That's okay, but you don't expect it to be a very sharp turn. Somehow that one tiny crystal of salt more would make you suddenly very unhappy. In economics, we typically think that change should be gradual instead of this like abrupt change. Similarly, think about profit. If you have a very sharp corner like that, it says that you're making money more money as you produce more, but at a certain point, suddenly your fortune reverses, and your money, not only are you not making more money, the amount of money you make actually goes down very quickly. It seems unreasonable to say that that's going to happen. Maybe you're not going to make as much money. Maybe eventually you're going to start losing money as you produce too much. But there's no reason to believe why your fortune would reverse so quickly just because you produce one single more iPhone, right? There's no reason why after you produce 1 million iPhone, the 1 million and first iPhone is going to crash the whole market and crumbles your profit. So in economics, once again, we don't think this is very reasonable as functional form. So we do not think that excluding these types of functions would be a big problem. We simply say that our functions are differentiable, and that excludes these cases. Another case we need to consider is the concept of continuity. So continuity is a very simple concept. It exactly means what you imagine. It's that a function is continuous at the point A if the limit of f as a approach 0 equals sorry, this is wrong. This is wrong. This is x approach a. Okay. The limit of f as x approach a equals fa. So this is what happens when you're lazy, and when I'm lazy and I don't want to, and I just copy and paste formulas from previous slides. So the limit of f as x approach a equals to fa. It's exactly what you imagine. If you have a function and this is the point A, what a function is continuous if the limit, so the trend you get from looking at the two sides are exactly identical to the actual point. So this is continuous. What is not continuous? this would clearly be not, this would clearly not continuous, right? This is clearly not continuous because if you look at the trend from the left-hand side and the right-hand side, they are different. So the limit does not exist to begin with, so this is clearly not continuous. But there are cases where the limit does exist, but it's still not continuous, like this case that we have seen before. This is a case that we have talked about before. The limit does exist in this case, but the limit does not equal to the actual point. So in this case, the limit exists, but it does not equal to FA. So these two cases, they are not continuous. But for different reason. For one reason, for the first case, the limit does not exist. For the second case, limit does not equal the actual value of the point. It does exist, the limit does exist, it's just not equal to the point. So it's not continuous. So in other words, continuity is what you imagine. The points are all joined together. The points are all joined together, then it's continuous. When you have a break in any way, then it's not continuous. What type of functions are continuous? Polynomials are continuous. Rational functions are continuous. Are there any rational functions that are not continuous? Yeah, no, I don't think so. So polynomials are continuous. Tangent is not continuous because tangent, as we have seen last time, it has vertical asymptote. So these are so in economics, once again, we typically assume functions are continuous because we don't think that it's reasonable to say there are sharp turns in how happy you are or how much money you make. A function is continuous if it's continuous at every point in its domain. That's a typical assumption in economics. And a function that is not continuous is not differentiable. Because you can see cases like these. You can see that in cases like these, right? What happens if you try to approximate the slope? Let's try. So a function that is not continuous is not differentiable. Let's try what happens if you try to approximate the slope. Okay, so what happens when you try to approximate a slope? Now I kind of intentionally draw it such that it looks like the slope of the two sides actually is the same, right? I kind of draw it like the slopes on the two sides are the same. So it seems like the slope on the left-hand side and the slope on the right-hand side should be the same, right? The slope does look like it's the same. But remember, what you're doing with what the derivative is the approximate slope at a given point. The limit of the approximate slope at a given point. So let's say this is your given point, right? This is your given point. What happens when you try to approximate the slope from the right? Well, no problem. If you're trying to approximate the slope from the right, you get actually, in this case, you get the accurate slope because I am drawing two straight lines. Right, so you do get an accurate slope. That's okay. But what happens when you try to approximate the slope from the left? You pick a point, you calculate the two-point formula, and notice that the slope is very different. Even though, in this example, I intentionally drew the two sides to have the same slope, That's not what the derivative is. The derivative is the approximation of the two-point formula, and with one of the point being the point you're interested in. And if there's a break along the point you're interested in, then one of the approximation is going to be something very different from the line, even if the two lines, you can see in this case, I drew it as if the two lines have the same slope. Right? So not to mention, if you actually have a case where they have very different slope, right? If they have very different slope, then you can see that this problem is going to be even bigger. Now this time I'm going to pick a point on the bottom, right? You're going to approximate the slope here, and then you're going to approximate the slope here, and you can see that the slope is going to be very different. So for the same reason, if you think about this line, it looks like, well, it's a straight line, except at one point. How come the derivative does not exist? It does not exist because if you use this point to approximate the slope, pick a point on the left, on the right hand side, you get a downward sloping slope. Pick a point on the left hand side, you get an upward sloping slope. So it does not work. The two-point formula, the derivative is ultimately depends on the two-point formula, with one of the point being the point you're interested in. So when you have a break, you are guaranteed to have different estimates of the slope, different approximation of the slopes from the two sides. One thing to note is that this relationship between continuity and differentiability goes only one way. Continuous function, a non-continuous function is non-differentiable. That's true. That's always true. But it's not. That does not mean that continuous functions are necessarily differentiable. That's not true. Okay, so not continuous means that it's not differentiable. This is basic logic, actually. That's true. Continuous means differentiable is not true. Not true. It's not true that all continuous functions are differentiable. And here's one example. This function is continuous because the idea of continuity is the limit of the function has to equal to the value at that point, or graphically, the function has to be joined together. There's no break. This function has no break. If you look at the right-hand side and the right-hand side, they all point to the same. They all go towards the same point. So this is continuous, but it's not differentiable at A. It's not differentiable because it's quite obvious that the slope on the two sides are never going to be the same. Right? So this is basically the search example I've shown you. So in economics, we typically assume functions are continuous and differentiable. That's the typical assumption you would read if you read mathematical models in economics. Assume that the production function is continuous and differentiable. That's a very common assumption. We need that because first we think it makes sense economically, and second, you need to assume it's continuous and differentiable because continuous alone does not guarantee differentiability. So you need to assume both. Well, typically, I would say you can actually just assume it's differentiable. So you could just say it's differentiable, but sometimes people like to write both of them. Okay, so these are functions that you cannot differentiate at that particular point. Finally, Notice that so far, we have never ever mentioned what A is, right? A could be any number in the domain of F. So there's really no reason we need to use A. You could equally use X. So f prime x equals to limit as h approaches 0 of fx plus h minus fx divided by h. You just replace A with X and nothing would go wrong. It totally works. This function is simply called the derivative of f without at a point A, right? This is simply called derivative of f. This function gives you the slope of f at any point of your choosing. The process of finding the derivative is called differentiation. Derivative is a function. Derivative is this limit, is a function. The differentiation is a process. It's the process of finding the derivative. Right. So in questions, like in exam questions, or like any questions requires you to do to find rate of change, you can either say, find the rate of change of f. That's the same as saying find the derivative of f, which is the same as saying differentiate f. They all mean the same thing. Right? One is quoting the actual target you're finding, the rate of change. One is quoting the mathematical formula, mathematical function you are using, derivative. The other is quoting the process, differentiation. The process is denoted by this notation, d dx, d over dx. Right? So we usually pronounce just d dx. This works just like any mathematical operator you have learned, like square root, or so it's an operator. So you put the operator d dx in front of a function that you're trying to differentiate. So d dx fx would give you the derivative. In meaning, it's identical. So this free stroke equal sign means identical. d dx fx is exactly identical to writing f prime x. They mean the same thing. You can use them interchangeably in all situations. Why would we have two notations for the same thing? You would see that in many cases, one is more convenient than the other, and in some other cases, you actually need one. You can only use one rather than the other. Now, in terms of convenience, you can see that the convenience of f prime x is that it's short, fewer symbols to write. On the other hand, in some cases, if you're trying to do something, you're trying to find the derivative of something very simple. Like, let's say I ask you, what is the derivative of x squared? We can answer that's d dx x squared. If you want to use f prime x notation, what do? You can't say x squared prime. That's not right. If you want to use the prime notation here, you will have to say, oh, you want me to find the derivative of x squared? Let fx equals to x squared, f prime x equals to blah. Right? So if you want to use the prime notation, you have to give a name to the function. You can't just say x squared prime. That's not correct. You have to say fx equals to x squared and f prime x equals to something. So for very simple differentiation, you don't want to bother with us giving names to all these functions, right? What if you need to do that? You need to find the derivative of dozens of very simple functions. Do you give names to all of them? You run out of alphabets. So in that case, it's easier to use the ddx. But in some other cases, when you have very long, one single very long function, you want to say fx equals to that function so that you don't need to write all the terms over and over again in every single step. Right. Finally, there's one reason why you need the ddx notation, is that in next term, you will learn multivariate differentiation. So in this part of the course, in this course, we always deal with functions with just one single variable, x, right? But there's no reason why a function can only take in one single input argument. You could have functions like f equals to x plus y, or f equals to x times y to the power c. You could have functions like that. And in that case, it's not clear what f prime x means when you have multiple variables that you can put into the function. So when you start having multiple variables, so f is a function of x, y, z, then you can't use the prime notation. You always have to use a ddx notation, because that's what makes it clear you are differentiating with respect to a particular variable. When that happens, you have ddx, ddy, ddz.